All right, welcome back, everybody. Welcome to Chapter 3 of Modern Mathematical Methods for STEM Majors. I'm Dr. Richardson. I hope you've been enjoying the lecture series so far. We're about to enter a longer chapter than one we've seen before, but it's a really important chapter. It's all about polynomials and rational functions. Let me pull up the slides and let's get started. Okay. All right, so just a quick overview of the whole chapter, all of chapter 3. The first section is all about lines and linear functions. That's the lesson we're going to do today. Next time, we're going to talk about factoring quadratic polynomials. That is the section that is literally just factoring quadratic expressions. So a lot of practice with that. Then we're going to talk about finding zeros of quadratic functions, then the graph of a quadratic function. Then we're going to broaden our horizons a little bit and talk about polynomials and this really important theorem called the Weierstrass approximation theorem. This is one of the things that sets this course apart from maybe a standard pre-calculus class. I'd like to motivate why we care about all these things instead of it just being something that you need for the next math class, for example. Like there's a reason that we focus on factoring quadratic polynomials, and a lot of it has to do with the fundamental theorem of algebra, and then you tie that together with this important theorem, which we'll get to in section 3.5. After that, we're going to talk about complex numbers, and we're also going to talk about algebraic numbers as well as transcendental numbers, because those play an important role in a lot of computer science applications. Then we're going to talk about how to factor polynomials and how that relates to the fundamental theorem of algebra. Remember, like I've said before, if a theorem has the word fundamental in it, you definitely want to know it well, all right? Then the last two sections of the chapter are all about rational functions. But in this chapter, we're actually splitting it up into two sections based on the behavior that we're going to study. So section 3.8 is local behavior of rational functions, looking at things like zeros, asymptotes, that kind of stuff. And then section 3.9 is where we look at the global behavior of a rational function, the asymptotic behavior, the end behavior, and then how to graph these things. So once we have all that we need to know about local behavior and global behavior, we can see the full picture of what rational functions look like. All right. Okay, now let's talk about this section 3.1. Just a little bit of a little bit of a warning in the beginning. This section is a little bit long. That's just because we're going to be covering a lot of stuff. The good news is this is stuff that many of you have probably seen already. So hopefully a lot of it is review, but maybe the way that we emphasize and de-emphasize certain things will make something you already know click even better than it did in the past. So there's basically three subsections to this section. There's the section on lines, where we'll cover all of this stuff, equations of lines, the three types of equations, parallel, perpendicular lines. Then we're going to shift gears a tiny bit and talk about linear functions. We'll talk about the average rate of a function. We'll talk about the characterization of a linear function. That's really important. And then we'll finish off the section by talking about systems of linear equations and how to solve them. One little note about this last subsection here. Uh, we're not going to do every possible example of solving a system, nor are we going to do every possible example of solving a system of linear equations. We're going to keep things simple and just boil it down to systems of two linear equations in two variables, which you'll see frequently throughout the calculus sequence and beyond. All right? Okay, now that the overview has been discussed, let's talk about lines. Where are you? Come here. There we go. Let's talk about lines first and foremost. So, one of the most fundamental geometric objects is a line. Literally, Euclid's geometry, one of the most fundamental objects is a line. Given any 2 points in the plane, or really just any dimensional space, those 2 points uniquely determine a straight line between them. Lines, linear functions, and just linear behavior in general are at the heart of a lot of approximation methods. Notably, they are at the heart of the derivative, which you're going to study at length when you get to Calc 1 next semester. All right. So let's start with some basic definitions. The definition of slope. I think many of you have heard of this before. If you've taken a math class in the past, your teacher should have discussed this with you intuitively. The good news is your intuition holds even still. So lean on it and use it to help guide you. So if you have any two distinct points in the plane, and then the line connecting those 2 points has the slope m, which is given by these expressions here. So the slope of a line is just the rise over the run. It's kind of like how much you're going up versus how much you're going across. And we can describe that algebraically like so. Y2 minus y1 over x2 minus x1. This is just giving you the change in y versus the change in x. That's really all it is. Change in y versus the change in x. And these are the y values of those 2 points. And these are the x values or coordinates. Okay, and then this is another symbol we use to indicate change. This little triangle symbol, it means delta. So you're going to hear that a lot in, man, this class, in calculus, in your STEM career. This is delta. Delta usually means change. So delta y over delta x, and that's just the slope, all right? Bottom line is slope is rise over run, so you can carry that with you at any point. Just think about it as rise over run. A little note at the bottom here, if the 2 points that you're working with lie on a vertical line, then we say the slope is undefined, okay? So on a vertical line, the slope is undefined. The reason for that is because delta x is 0. If you're on a vertical line, then the x coordinates of the 2 points are the same. So when you take their difference, you're going to get 0. And you can't divide by 0, so we say that the slope is undefined in this case. All right? Okay, let's practice this. And this is one I do want you to try on your own. So I just want you to find the slope of the line connecting these 2 points, and then I want you to graph the line, okay? So as always, think about it for a moment. All right. Then you know what you got to do next. You got to speak out loud. Remember, you don't need to say it to anybody. You can just say it to yourself, to your dog, to your phone, to your computer. Don't feel weird about talking to yourself. It's normal and it will help your brain make sense of things. So say something out loud. Okay, now try to work it out on your own. Find the slope of the line connecting those 2 points and then graph the line on a plane. All right, now let's do it together. So first thing is you got to pick which point you want to call the first one and which point you want to call the second one. The good news is it doesn't matter which one you choose to be first or second. The slope calculation will come out the same either way. The only catch is once you choose which is the first, you have to stick with that one being the first. So you can't swap x and like the first x and the second y and that kind of stuff. So I chose to call this point here the first one and this point here the second one. So we're just going to run through the calculation. Slope is change in y over change in x. So y1 is -1, y2 is -3. Notice the use of parentheses here. Parentheses are your friends. They help you group things. They help keep your focus, all right? So here we're subtracting a negative. So I'm including parentheses to indicate that very, very explicitly. Down here, 3 minus 2. And then we just go through the arithmetic. -1 plus 3 over 1. That's 2 over 1. That's 2. So the slope is 2. Now let's graph it. Let's graph it. So we know that the rise over the run is 2, and we can write 2 as 2 over 1. We're also given a couple of points. So you've got some options. You could choose both of those points, plot both of those points. There's this one, and then there's, where is it? Wait, hold on. Is this the right one? 3. Hold on a second. Wait a minute. Oh, yeah, there it is. Getting lost in my thoughts. Okay, so you could plot both of these points like so. Or you can use the slope to help guide you. So plotting the second point, actually, let me just draw it on here. 3 comma -1 is right there. So you can plot those 2 points and connect them with a line, or you can use the slope to help you. So you can start at one of those points. Oops, hold on, there we go. You can start at one of those points and then you can count up 2 and then to the right 1, and that will help you locate another point. All right, just like that. So one thing I want to point out about the slope is that the slope is basically telling you the direction you want to travel from any point given on the line. So you can interpret the slope as a two-dimensional vector, just like this, right? Just like this. It's basically the run. Oh, oops, sorry, these are backwards. Let me fix that. This should say 1 comma 2. There we go. I'll fix that after the recording. 1 comma 2. So you're basically going up 2 and to the right 1, and that'll give you that correct slope. So you follow that direction. All right. So slope, now let's talk about vertical lines. We're going to see these a lot, especially when we start talking about rational functions, because asymptotes, vertical asymptotes of rational functions are vertical lines. So let's talk about the equation of a vertical line, and let's talk about the vertical line as a set. Oh, hold on just one moment. All right, sorry about that. Okay, so a vertical line passing through the point a comma y is for a fixed number a has the equation x equals a. So what this says is that the x value must be equal to a, but y can be any number. Y is not included in this equation, so y can be whatever you want it to be. It's not present in the equation. Now you can describe it as this set. This is a set of points in the plane. Remember, this is that set builder notation, right? So these are the points in the plane R2 such that x equals a. And here again, you can see y is what we call a free variable. Y can be whatever you want it to be. Right. Okay, so now let's talk about some equations of lines. For a line that is not vertical, there are three important forms of the line that we can use to represent the line. Which one we use? Well, just depends on the context that you're working in. So don't feel compelled to use only one of these. Use the one that is the easiest to use given the context of your problem or your application. So the first one is point slope form. The second one is slope intercept form. And the third one is standard form. And we're going to go through all three of those right now, starting with point slope form. So an equation of the line with slope m passing through the point x1, y1 is given by this equation here in the box. Y minus y1 equals m times x minus x1. Now here, the x and the y, those are the variables. Those are the things that are changing. X1 and y1 are fixed numbers. Those are just the coordinates of this point, right? So we've got two or three, I should say, fixed numbers, and then we've got two variables here. All right, now, a couple notes about this particular form. You can produce this form immediately, like instantly, when you know a point and the slope. So if you know the point and a slope, use it. And I'm saying that very, very, very emphatically. Use it. If you know a point and you know the slope of the line, just use this form. You don't need to do any more manipulations. This is a valid form of a line. Maybe more specifically, I'll say you don't need to write everything in slope-intercept form. You don't need to write every line as y equals mx plus b. This is a valid form of a line. And I encourage you to get comfortable with this form because it becomes more relevant when you get into Calc 1 and Calc 2 and Calc 3. The reason is for this. So this form is really great when you want to look at linear behavior locally. In other words, if you want to look at the behavior of something near a point and you want to look at linear behavior near that point, or even if you want to graph the line by hand, this is a great form for that. There's a reason. The reason is because when a line is written in this form, we can instantly see a point on the line, and we can instantly see the slope of the line. Instantly, just by glancing at it, we get all of that information. And what happens a lot in calc is our attention becomes localized around a point. There's basically a point on a graph, and we're going to zoom into that point as close as we can, and we're going to see how the graph behaves right around that point, as close as we could zoom in. That's why this formula is great for that kind of exploration. Um, here's an example. This is what I had shown on the previous slides. Here's that point 2, -3. We can count up and go over 1, and that'll be another point on the line, and then we have the full line, just like that. So this is that line written in point slope form. And once again, this is a valid form of a line. You're done. You can write in that form and stop. You're good. Okay, now let's talk about one that you're probably maybe more familiar with, slope-intercept form of a line. Yeah, slope-intercept form of a line. So let's start with this. An equation of the line with slope m passing through the y-intercept 0, comma b is given by this equation here. Now, in this case, x and y are variables again, and b is a fixed number called the initial value. M is also a fixed number, that's the slope, right? But the difference now is b is kind of a special number. It's what we call the initial value of the linear function, which we'll talk about in a minute. Here's an example of graphing one using that form. We have the y-intercept, 0 comma 4. We have the slope. Slope is negative 3. So we're going to go over 1, down 3, and there it is, just like that. Okay, couple notes about this form. So this is how you write a non-vertical line as a linear function, which we're going to talk about in just a couple minutes here. Mx plus b is well, the basic form of a linear function. So when is this form helpful? This form is helpful when you know the slope and you know the initial value of the linear function, basically the starting value. And if you want to graph it by hand, starting at the y-axis. But I want to emphasize this down here because I notice this a lot whenever I talk about lines and work with students in exploring lines. Don't feel compelled to always write a line in this form. Um, I know it's popular, at least in American high schools, to emphasize this form to the death and just grind it into students. But this is not the only form of a line, and it may not be the most relevant form of a line, especially depending on the context. So, to give you an example, this formula is really helpful when you know the y-intercept, right? You know the y-intercept, you know the slope, you can construct the line using that information. But if we are, say, exploring some function, sorry, some graph of a function, maybe it looks like this. That's pretty good. Okay, what if we wanted to focus all of our attention on this point right here? Imagine zooming in on that point with your eyeball. Zzzz. Okay, zoom in on it. Well, maybe we want to study the potential linear behavior when we're near that point. So maybe we want to look at a line that just touches the point right there. So if I want to describe the red line that I just sketched, I want to use point slope form because I've got a point and I can find the slope of that line, hopefully. What I'm not so interested in is the y-intercept because the y-intercept is way over here. You see what I'm saying? So this y-intercept, this b value, is way out of the way from where my focus is. So this particular form of a line may not be the form that you want to use. It just depends on the context. And if we're talking about localized behavior, we don't want our form to have this information that's possibly very distant and far away from where we're focused. So just bear that in mind. Okay. Um, oh yeah, yeah. So I kind of said this already. In essence, this form says to start at the y-intercept and then move in the direction of m from that point, i.e. in the direction of the slope vector if you write it as a vector. The other cool thing is this. This is another reason why I tend to prefer the point slope form. This slope-intercept form falls out immediately if you use the point slope form given the y-intercept. So check this out. If you know the y-intercept and you know the slope, that means you know the point and a slope. You could use point slope form and slope intercept form just drops out instantly. Here we go, right? I'm using slope intercept. I'm sorry, I'm using point slope form here. The point is 0 comma b. But when we simplify this, this is just 0. So this just becomes mx. And we can add b to both sides and we get slope intercept form. So once again, point slope form is kind of superior in this way. Okay, next form is the standard form of a line. So the standard form of a line is given in this structure right here, where the numbers A, B, and C are constants. Those are fixed values, okay? Now, this form is really, really helpful for computers and when you want to do linear algebra because of its structure. This form is also common when we're solving systems of linear equations, which we'll see in a few minutes here. Uh, because the structure lends itself to easy computational manipulations. And these are manipulations that you will automate in a linear algebra course, hence the words linear and algebra. Without getting too far off track, linear algebra is the study of linear mappings and systems of linear mappings. Basically, think of them as linear equations, right? So pretty much once you get to maybe 3 or 4 variables, you're going to want to use linear algebra techniques. Many of you who are STEM majors are going to have to take linear algebra. I hope that you do. It's a really, really fascinating course. It's amazing what you can do with linear algebra. It's also at the core of a lot of modern math and science. If you're interested in machine learning and AI and things like that, linear algebra is a fundamental component of those theories. Okay. Um, Oh yeah, yeah. Here you go. This form is also very handy when the number of dimensions gets large, which is where many of you are going to be headed mathematically. You're going to want to study systems that have a large number of dimensions. Little note at the end here, in this form, the slope of the line is negative a over b, and the y-intercept is 0 comma c over b. You can get that same result just by solving this equation for y. If you solve this equation for y, then you have written it in slope-intercept form. Yeah, you can work on it on your own if you'd like to try. Just solve this for y, and you'll see that it's in slope-intercept form. Okay, here's another line using the standard form. So the y-intercept here is, oh, here's the line right here, 2x minus 3y equals 9. The slope, right, is going to be negative or negative 2 over negative 3. So that's going to give you 2/3, right? So up 2 over 3. And the y-intercept is 9 over negative 3, which is just 3. There you go. So that's another way you can use that form. Right. Now, that being said, those are the three different forms of a line. Let's talk for a minute about parallel and then perpendicular lines, starting with parallel lines. So, two lines in the plane are parallel if and only if they have the same slope. Have the same slope. So whenever you hear the word parallel, I really, really want you to marry those two ideas in your head. Parallel means same slope. All right. That is what parallel means, and that is what same slope means. If two lines have the same slope, they're parallel. If two lines are parallel, they have the same slope. Equivalence. All right. So geometrically speaking, we're doing a lot of the bouncing between algebra and geometry here. Non-vertical parallel lines are just vertical shifts of one another. So, for example, let me draw a quick plane here. This is X, this is Y. Let me draw a line here. Okay, here's this line. I'm going to use my technology here to cheat a little bit and duplicate it. So these two lines are parallel. What is the difference between those two lines? They're just vertical shifts of each other. So this lower line right here is just this line right here shifted down a little bit or shifted up a little bit. So parallel lines in the plane, at least non-vertical parallel lines in the plane, they're just vertical shifts. That's it. So that's why the slopes are the same. You notice that the direction here, the direction of the lines is still the same. The direction has not changed. The slope has not changed. What's changed is the initial value or wherever the line is going to start or a point on the line. The set of points can be different. That's the idea. Okay, so that's parallel. You've got that same slope. Now let's talk about perpendicular lines. Perpendicular lines are different. There's a big difference between parallel and perpendicular. So two lines in the plane are perpendicular or orthogonal if their slopes are opposite reciprocals. Okay, opposite reciprocal slopes. One thing I want to mention here, the word perpendicular and the word orthogonal, they are equivalent. They mean the same thing, right? This is just a more general version of the word perpendicular. And when two lines are perpendicular, that means that they intersect at a right angle. And a right angle just means a 90-degree angle. I'm assuming most of you have heard of that before. We will talk about right angles and 90-degree angles in chapter 6 a lot, but that's basically it. So when you think of perpendicular, think of right angles. That's what it is. Now, more specifically, more algebraically, I'll say, if a line has slope m, then the line perpendicular to it must have the slope -1 over m. So we're doing opposite reciprocals. Let me just emphasize that here. Opposite reciprocal. You see that? I tried to color code it the same, but perpendicular means those two things. If you don't have those two things, you don't necessarily, I mean, you don't have perpendicularity. So opposite, oops, opposite and reciprocal. That's how you get the perpendicular line. All right, let's practice for a minute. I want you on your own to find the equation of the line perpendicular to this line here and passing through the point 1 comma 5, okay? So think about it for a second. Okay, now got to do it, got to say something out loud about what you would do to start. How would you find the equation of this perpendicular line you're looking for? Right. And now work it out on your own, and we'll do it together in just a moment. Okay, here we go. So if I need to find the equation of a perpendicular line to this one, well, look, this line is already given in point slope form, so we can immediately pick out the slope. Let's get the slope. The slope is -2. Sweet. And we're also given a point on our new line, 1 comma 5. Oh, this is great. So we have a point. We're going to know the slope of our perpendicular line. We can use point slope form, but we need to find the slope of the perpendicular line first. So remember, if the line's supposed to be perpendicular, we need the opposite reciprocal of this number. So we need -1 over -2, which is equal to 1/2. So that's the slope of our new line. -1 over -2, which is 1 over 2. And we've got a point. Now that we know the slope, we know a point, we can use point slope form, and we're done. Voila, there it is. Instant. Another thing I want to remind you of, you can leave it in this form. You can leave the line written in that form. You do not need to solve it for y. You do not need to write it in slope-intercept form. You can leave it in this form. This is a valid form of a line. You can dust your hands off at this point. You're good. All right? Okay, now let's shift gears a little bit and talk about linear functions. So previously we were just talking about lines, types of lines, equations of lines. Now let's bring things into the realm of functions. We spent all of chapter 2 talking about functions, so hopefully you're a little more comfortable with them now. If not, we're still going to get lots of practice throughout the rest of the course. So here we go. Let's talk first about the average rate of change of a function, and we're going to see how that's related to linear behavior. So consider an arbitrary function, just any random function, y equals f of x, and let 2 points, x1 and x2, be in the domain of the function f. We often want to ask ourselves these two questions when we're given this information. One, how much does the output f of x change between x1 and x2? How much does the output change between those two values? And then the second question is, how fast does the output change between those two values? So in other words, we want to know, what is the average rate of change? All right, the average rate of change of the outputs. So to talk about that, we're going to need a couple definitions, and then we're going to get a very, very familiar formula for this. So we need to talk about increments, which is a, a fancy way of saying the change in x and the change in y. So given real numbers x1 and x2, with x1 less than or equal to x2, just looking at the order of the two numbers, then we say the change in x, or in other words, the increment of x is delta x, and that's just x2 minus x1. Same thing we saw when we talked about slope. Now, because we're talking about functions, if there is a change in the input values, there is a corresponding change in the output values, and we call that delta y. So this is what we call the increment, and then this is the corresponding change in the output values. All right? So that's what we mean when we say increment. Okay, now, what is the average rate of change of a function? This should look very, very familiar. So the average rate of change of f of x with respect to x over an interval x1, x2 is given by an important expression that we call the difference quotient. Okay, and the difference quotient is literally the slope. That's what it is. The difference quotient is the slope formula. More specifically, it's this expression right here, this calculation, f of x2 minus f of x1 over x2 minus x1. We're going to talk about the difference quotient at length here, but I just want to emphasize that if you ever hear somebody talk about this, they mean the slope formula, okay? Difference quotient means the slope formula. The slope formula has many different structures. We've already seen a few of them. We're going to see a couple more right now. It really is just different ways of writing the same expression, but different ways of writing things can be helpful depending on the context, right? That's the kind of the moral of that idea. Right. Let's now that we know what the average rate of change of a function is, the slope between two outputs, well, I guess between 2 points on the graph, I should say. Well, let's do a word problem related to it. Okay. So the US national debt in the year 2015 was $18.5 trillion. Dollars. In 2025, at least this year as of right now, it's $36.2 trillion. Dollars. So my question to you is, what is the average rate of change of the US national debt over this time period? All right. So this is one where you should think about it for a minute. Oop, where is it? There it is. Okay, think about it for a minute. All right. And now give yourself some of that audio feedback. Say something out loud. Maybe what is the formula for the average rate of change? Okay. Now write it out. Try to do it by hand. Do not use a calculator and try to do this all by hand. You can do this by hand. Try it without a calculator and we'll do it together in a moment. All right. Okay. Let's do it together. So let's be a little bit specific here. We're going to create a function relevant to our current scenario. So we're going to create this function d of t, and we're going to let it represent the US national debt at time t, where t equals 0 corresponds to the year 2015. So the input of this function is a number t, and the output is the national debt at that, well, at that time. So in this case, t equals 0 corresponds to 2015. So that means t equals 10 is going to correspond to 2025, 10 years later, right? So what do we know now? We know that at time zero, the national debt was 18.5 trillion. We'll keep the scale off to the side. Just remember these numbers are in trillions, and then we'll hold that off. So, I'm sorry. D of 0 is 18.5, and D of 10 is 36.2. And if we want to know the average rate of change of the US national debt, we just need to compute the slope. We need to compute the difference quotient, change in y over change in x. So here is the change in the debt. Here is the change in the years. 10 minus 0 is 10. This is d of 10. This is d of 0. Do that subtraction. Try to do it by hand. You don't need a calculator for this. Just use the fundamental intuition we talked about back in chapter 1 and use place values. Use the decimal system. And when you do this, you're going to get 17.7. And again, appeal to that fundamental intuition. This is 1/10 of 17.7, right? So really, we're just moving the decimal point one spot to the left, and we get 1.77. So what that means is the national debt increased on average by about $1.77 trillion per year during 2015 to 2025. That's the idea. Um, I don't have it written here, but one thing I want to mention here is this is only an average, right? This is not exact every year. So it's not that every single year the debt went up by 1.7, 1.7, 1.7, or 1.77, 1.77. This is just the average rate of change. There are some years where the debt went up a lot, and there are some years where the debt didn't go up very much. It just kind of stayed, right? So this is just an average over an interval. It's not the exact change at every moment in that interval. Just want to be clear about that. Right. Now that we have this idea of average rate of change, we need to talk about something called secant lines. These are, hey, come on, there we go. These are going to play a really important role in Calc 1, including the formulas that you see here. So I want to go through them all, clarify them. If you have questions about them, please ask in class, and we will go over them in great detail. You want to be really comfortable with these. So, what is a secant line? A secant line to a curve is a line that intersects the curve more than once. That's it. Now, suppose we're given a curve, y equals f of x, then the secant line passing through these 2 points has this slope and has this equation. Okay, we're gonna sit here and ruminate about this for a little bit. One thing I want to remind you, remember, we're plotting outputs vertically and inputs horizontally. So this is the point x, comma y, where y equals f of x. That's the output of the function f, right? So input x, output f of x. Input a, output f of a. And these are both points on the graph, and you can see the picture right here. I'm going to zoom in on this in just a moment. But Putting all these things together, we need to synthesize some ideas here. We've got 2 points on this curve that you see right here in black. We've got 2 points. Here's one, here's the second one. All right. We can find the slope of the line connecting those 2 points. It's the difference quotient, right? It's just the same formula. Change in y over change in x. The rise over the run, still the same. That is the difference quotient. That is the slope. So the slope of this secant line is given by the difference quotient. Now, this might start to make your brain go, "Ugh," but don't worry. Look at the structure. Don't let the individual symbols overwhelm you. Look for structure and emphasize the conceptual understanding here. I'm gonna try to like mush some things. First, let me do this first. First, this is the equation of a line. It's in point slope form. That's all it is. The slope is m. What is the point on that we're using to describe the line? The point a comma f of a. There it is. So we've got a point and we've got a slope. We're writing this equation in point slope form. There it is. Now we have a more explicit formula for the slope given by the difference quotient, f of x minus f of a over x minus a. So we can replace m with that formula. And then we get this thing. Looks complicated. Maybe by visual inspection, it's complicated, but it's just the formula for a line. It's the formula for the secant line. Now, what I want to do is zoom in on this picture a little bit and talk about some pieces. So let me do that here. Let me get to the, let me zoom in a bit. That's a bit better. Okay. And I can kind of keep this in. Uh, a little bit. That should be a little better. Okay. All right. So let's look at this picture because this picture is one of the fundamental pictures that you're going to see in Calc 1 and beyond. So let's talk about it. Oh, wait. Hold on one second. Oh, give me one more second. Sorry. All right. Okay, there we go. Sorry about that. Okay, so let's look at this picture. First, this black curve you see, that is the graph of the function y equals f of x, okay? So that's like the function we're working with. Now, let's look at the 2 points that we picked on this graph. There's this point, x comma f of x, and there's this point, a comma f of a, right here. All right. Now we're going to connect those 2 points with a line, a straight line. That's what you see right here. That is the secant line. So that line connecting those 2 points is the secant line. And now we're just going to pick apart all these pieces and look at each individual piece. For one, there's a change between the x coordinates here. It's the length of this, or I should say we'll just say the length, but it could be backward, so the signed length of this horizontal line. This horizontal line is given by delta x, x minus a. So the distance between here and here is x minus a because that's the difference between a and x. All right? And that's what we call delta x. Now compare that to delta y. So delta y here is the change in the function values, right? So here's f of a, here's f of x, and what we're looking at is the change between those two values. It's right here. That is delta y. Delta y is the change in the outputs of the function. Boom, there it is. That's delta y. Okay, what is the slope? Remember those pictures, those figures that I showed earlier, there was like a horizontal line and a vertical line, and you kind of walked your way across those lines to get to the next point. Remember, the slope is rise over run. It's change in y over change in x. It's delta y over delta x. And that's how we're getting it. So that's the slope of the secant line. And that's why this all looks the way that it does, right? Okay, I hope that's clear. Um, Now I want you to stare at this for just a second. So this is one where I want you to stare, and we're going to change things up just a tiny bit. So keep staring for a second. All right, still staring? Okay, good. Now, the truth is, it's often more convenient to re-express the difference quotient in terms of a single value, x equals a, and the increment h. H in this case is equal to delta x, all right? So we're going to look at this picture some more, but what I want to show you is how we are just changing the structure of the difference quotient. Let me emphasize this. No values have changed here. The line has not changed. The function has not changed. The points have not changed. The slope has not changed. The only thing that is changing here is how we label things. Because sometimes you could think of it as a glass half full versus glass half empty situation. Sometimes it's easier to say, oh, the glass is half full. Other times it's more meaningful to say the glass is half empty, right? That's what we're doing here. The volume, the amount has not changed at all, only the way we are expressing it. So the slope was given in this form, but now what we're going to do, let me zoom in again. Oops, there you go, zoom in again. We're going to rewrite, we're going to rewrite delta x as this length here, which is h. Okay, so what we're doing is we're letting x minus a be equal to h. So now x minus a is equal to h, and this is what it looks like. So what I want to do, hold on, maybe I can, yeah, I want to flash back and forth between these two representations for a minute. Okay, just keep your eye on the picture. Okay, and then we're going to talk about it in a second here. Keep your eye on the picture. All right, now let's go through the pieces just like we did a second ago. First, down here, delta x is x minus a. We're just going to call h x minus a. There it is. All right. So if h is x minus a, then this point here is a plus h. Let me go back. See, x is a plus h. There it is. You see it? X becomes a plus h, just like that. So now we can write delta x as the difference between these two values, a and a plus h, but the difference between those two values is just h. Boom. There it is. X minus a is h, same thing. Now we're going to do the corresponding change in y, right? So here, remember this is the change in y, f of x minus f of a. There we go. But remember, we rewrote x as a plus h, right? X is now a plus h, just like that. Just like that. F of a has not changed. We didn't change a. We didn't change that like starting value, right? We just changed the second value by talking about it in terms of adding a certain amount. So this is f of a plus h minus f of a, and that is the change in y. There we go. Pretty cool, huh? So this is just a structural change. Like I said, there's no value change. All we've changed is the structure. But sometimes this is a better structure to use. So sometimes this structure for the difference quotient is acceptable. Other times this is more preferable. And there's a reason for that. This one only involves, well, two constants, I'll say, A and H, right? So here you can talk about this as a and then a plus h. So it kind of localizes everything to the point a comma f of a, localizes everything here. And you're going to do that a lot in Calc 1. All right. Okay, I know that's kind of complicated. Please ask questions about it and we can go over it in more detail. Just make sure you're comfortable with this picture and these two equivalent forms because you're going to see them a lot in Calc 1 and beyond, frankly, and beyond. Okay, let me get back to these. Um, Yes, okay, so now we can equivalently express the average rate of change of a function using this formula instead. And this is honestly just a copy paste of the previous definition of average rate of change of a function, except now I'm including both forms of the difference quotient. Here was the first form we saw, here's the new form, just like so. And now the interval is a comma a plus h instead of x1, x2. In this case, x2 is a plus h. That's the basic idea. All right. Now, I will say this. Using this form, using this new form of the difference quotient, I want you to try this problem. I want you to compute the difference quotient for this function on the interval x comma x plus h. All right. So this is one where you should think about it for a minute. Hmm, hmm. Okay. Now, say something out loud to your dog, to your cat, to your hamster, to yourself. What are you going to do first? I always like to start there. What am I going to do first? Okay. And now try to work it out on your own. Just a little heads up, it will be a bit calculation heavy, so I strongly recommend you write your calculations as a chain of true equalities, okay? You'll see why in a moment when we do it together. Okay, here we go. So, difference quotient. So the difference quotient in this case is going to be this. This is how I would start. Um, G of x plus h minus g of x over h. All right, so I need to compute all of these pieces. Good news is I already know g of x. G of x is this expression right here. But I don't know g of x plus h yet. To compute this, I need to take x plus h and plug it into this formula and then do some simplification. So I think I'll start with that. G of x plus h, everywhere I see an x, I'm going to replace it with x plus h. There we go. Now I'm just going to do some arithmetic, right? I'm going to FOIL this out. I'm going to expand this using the distributive property. I'm going to distribute this -2 to both of those terms, and I get this to start. Remember, take as many steps as you need. Don't feel like you need to go from this to the final answer. You don't need to do that. You can take steps, all right? So here I FOILed this out to get that. I distributed the -2 to get that. Now I'm going to distribute this 3. That's the kind of thing that if I try to do both of these steps at once, I will mess that up. That's just me. I'll mess that up. So I like to add, give myself a little leeway, a little flexibility, and do them one step at a time. So now I'm going to distribute the 3 to those. There, there, there. So this is g of x plus h. Now we know g of x plus h, we know g of x, we know h. So now we can compute the difference quotient. Here we go. This is the messy part, but remember, don't let it overwhelm you. You control the math does not control you. Just take a deep breath and let it out, and just follow your nose. Walk step by step through each piece very carefully, taking care, and write everything as a chain of true equalities. Trust me. Organize your work that way. It makes it easier to debug your calculations. So here we go. Actually, I'm going to highlight it just so everyone can see. G of x plus h is this. And then g of x is this. One thing I want to point out here is I used parentheses. Parentheses are your friends, okay? Use parentheses. They will group things. They will keep you focused. They will prevent you from making errors. Because again, here we're subtracting the entirety of g of x, not just the first term or the second term or the third term. We're subtracting all of the terms of g of x. So we need this negative sign to apply to the entire expression, 3x squared minus 2x plus 3. All right, so I'm going to distribute this negative to all three of those terms, and I get -3x squared, positive 2x, -3. Now the numerator is a big mess. It's just a giant mess. Don't worry, just walk through it piece by piece and see if you can cancel anything, if you can simplify anything. In this case, we can. So we can cancel 3x squared, because look, there's a positive 3x squared and a -3x squared out. Now, there's also a 2x here and here. This one's negative, this one's positive, so they cancel out. And then same with the threes, +3, -3, cancel those. And that's like, you should embrace those moments and just enjoy them. One of the best parts when doing these types of computations is canceling things, just being like, okay, they're out. So once all this stuff gets canceled, this is the numerator, which is not nearly as bad as it was one step earlier, right? Um, Now we're going to look for common factors. There's some similarities between all of these terms. Each one of these terms has a common factor of h. So that means we can factor out that common factor of h. H comes out, h comes out, h comes out. There it is. This is what remains. And the reason we did that is now we can cancel the h just like that. Remember, when you're canceling, you can only, or, I'm sorry, canceling through a fraction bar, you can only cancel factors. You cannot cancel terms. Beware. We'll talk about that more as the course goes on, but we can cancel those h's because here this single term has a factor of h in it, and this single term has a factor of h in it. So we can cancel it because that's just going to be equal to 1. And then lo and behold, That is the final result. That is the simplified version of the difference quotient for this function on the interval x comma x plus h, just like so. Right. Yeah, there we go. So what this is doing, this is kind of handy. This is like a formula that we can use. This means that for any point x in the domain of G, given any interval of length positive h, we can find the slope of the line between the endpoints of the function on that interval, which is pretty cool. So give me any input you want for that function, any input in the domain. Give me an interval of any length h that you want, and I can tell you the slope of the secant line that connects those 2 points. I can tell you the average rate of change of the function between those 2 points just using this formula. That's all it is, just using that formula. How cool is that? Super cool. Okay. So that's average rate of change. Now, let's talk about something important about a linear function. Let's talk about the characterization of a linear function. So we will see something similar to this in chapter 4 when we talk about exponential functions, but the characterization of a linear function is essentially the behavior that a linear function exhibits that defines it to be linear. So characterizations can often be taken to be an equivalent definition. All right. So this is the characterization of a linear function. F is a linear function if and only if, for any real number x, there exists a constant m, a real number m, such that f of x plus 1 minus f of x equals m. Okay, that is the characterization of a linear function. We can rewrite that equivalently as f of x plus 1 is f of x plus m. Okay, that is the characterization of a linear function. So what does this mean? It means these 2 points right here. The difference between unit consecutive outputs is constant. Constant. So if you want to keep moving one step in the x direction, you're going to keep moving m steps in the y direction. Put another way, if you want to produce f of x plus 1, you just take f of x and add m to it. And you can do that repeatedly, okay? Um, do I have, well, I've got an example coming up next, but this is a good time to just ponder this for a minute. So let me show the thinker. I just want you to reread this to yourself and kind of think about what it says. Okay. Okay, now let's do an example with it, all right? So to the right over here, there's a table of inputs and outputs of some function f. We don't know the formula for it, we just know these values here, these outputs. What I want you to do is I want you to use the characterization of a linear function to determine if this function is linear or not, all right? So think about it, think about how you would do it, okay? Right? Now, say something out loud to yourself. What could you do to determine if this thing is linear or not? Okay, now work it out on your own. Use that characterization, compute the difference between the consecutive outputs, and we'll do it together in a moment. Right, here we go. So, just to refresh our memories, well, a function is linear if the difference between unit consecutive outputs is constant, right? So that means these are unit consecutive inputs. They're increasing by one, right? Plus one, plus one, plus one, plus one. So a function will be linear only if the difference between these outputs here is the same number if it's constant. So we're going to compute the difference between these two, and then these two, and then these two, these two, and these two. And we're going to see if we get the same number every time. Here we go. So f of negative 1 minus f of negative 2, right? Unit consecutive is 1 minus negative 1. So I'm doing 1 minus negative 1, and I got 2. Now I'm going to do the same thing here. 3 minus 1 is 2. Okay, good sign. 5 minus 3 is 2. Okay, same number. I'm getting the same number. 7 minus 5 is 2. 9 minus 7, oops, 9 minus 7 is 2. We're getting the same number every single time. So because this number is the same every single time, that means that f has to be a linear function by the characterization of a linear function, all right? So we've basically shown that the difference between unit consecutive outputs, I'm sorry, the difference in outputs between unit consecutive inputs is constant, and it is the number 2. The good news is that number 2 is literally the slope. That's the slope of the line. So guess what? We have the slope of the line. We also have the initial value right here, right? Remember, the initial value is when x is equal to 0, and that's going to be 3. So we have the slope, we have the initial value, we have slope-intercept form of a line. Boom. There it is. So this is the formula for this linear function if you wanted to extend it to all real numbers. That's basically it. Slope, intercept, slope-intercept form of that linear function. Cool stuff. So that's the characterization of a linear function. Now, because of that characterization, we have this really nice corollary, and it's this. It says linear functions have a constant rate of change. Okay? And now consequently, they have a constant average rate of change. So that means the average rate of change of a linear function is a constant over any interval. Moreover, if you're given a linear function in this form, slope-intercept, the rate of change is the slope of the line. All right. So ponder this for just a second. Ponder that for a second. And maybe I have to admit that this sounds almost a little too obvious, right? Where you're like, well, yeah, they have a constant rate of change and the constant average rate of change because of the slope and yada yada yada, right? Well, we're going to prove it, but we're going to prove it in activity. So that's going to be one of your activity problems when we do that in the activity, right? You're going to prove that they have a constant average rate of change. If you want a hint for how to do it, use the formula for the average rate of change and see what you get. Okay. All right. So that covers lines and linear functions. Now we need to talk briefly about systems of linear equations. All right. So if you need to take a break, I know I've been going for a while. Now's a good time to take a break. So maybe we'll do that. Stretch a little bit. Oh, okay. All right. Okay. Now we're back. So systems, that's right. Okay, systems of linear equations. So a lot of equations of interest in science and math are linear in structure. We know a lot about lines, and I think if you remember, if you studied these in high school or in a previous math class somewhere, you've probably spent a lot of time on lines. There's a reason for that. A lot of times we compute linear approximations of more complicated functions, and we leverage everything we know about lines to get more information about a function or maybe get easier information about a function. So linearizations are studied at length in Calc 1 and 2 and 3, and they're one of the most important concepts in calculus. Um, Gosh, I mean, the derivative is essentially a local linearization. You could think of it like that. And the derivative is something that you study fundamentally in Calc 1 and Calc 2 and Calc 3. So there's that. There's also linear algebra, and linear algebra revolves around the study of linear maps, like I mentioned earlier. Their properties, how to operate on them, and you're going to learn algorithms for solving systems of linear equations in many variables. So we're not going to do that here. We're not going to generalize everything to the nth dimension, right? We're going to keep things pretty simple. But let's start with just defining what a system of equations is and a system of linear equations. So a system of equations is just a collection of two or more equations, each containing one or more variables. So when you think about a system of equations, I just want you to think of a list of equations. Could be any number of variables, any number of equations. That is a system of equations. What is a system of linear equations? A system of linear equations is a system in which the equations are all linear in structure. right? Equations can have all sorts of crazy forms, right? We've already seen a bunch of kinds of wild kinds of equations. You could form a system, right? And one of the bigger questions in math is, can we solve that system? Well, the good news is if it's linear, if the equations are all linear, you can solve it, and we have a lot of amazing algorithms to do so. All right. Um, what does solving a system of equations involve? It just involves manipulating and combining the equations in valid ways to solve for the unknown variables. Um, yeah, like we've seen previously, when we're solving single equations, there may be no solution, there may be a single solution, there may be multiple solutions, or there may even be infinitely many solutions. So if you're solving a system of equations, any of those are possible. Okay. Um, but what we're going to do is this. So I want to be clear about this. We're going to restrict ourselves to solving systems of two linear equations in two variables. That is as far as we're going to go. We're not going to do three equations and three variables, four equations and four variables. That kind of stuff is better suited to a course in linear algebra when you get more generalized and frankly, just simpler techniques for solving these types of things. So all the linear equations, or sorry, all the systems of linear equations we are going to explore have this structure right here. AX plus BY equals C, DX plus EY equals F. Geometrically, right, we've got the algebra. Let's look at the geometry, algebra and geometry, BFFAE. Each one of these equations represents a line, as we saw earlier in the section. And what we want to know is, do the lines intersect? Do these two lines intersect? So what are we going to do? Well, we're going to assume that they do intersect somewhere, and then we're going to attempt to solve the system of equations. If they do intersect, solving this system will give us the location of the intersection. All right. That will be the solution set will contain the point or points where they intersect. Okay. Um, oh yeah. So for this particular application of systems, the standard form of a line is usually the easiest. It's the best place to start. And also because we're only working with lines and we're not working with any general function, there are only three possibilities for a solution. One, the lines do not intersect. That means there's no solution to the system. The lines intersect at a single point. That means there's one solution to the system, and it will be in the form of a point in the form x comma y. Or the lines completely coincide. That basically means the two lines are the same line. And if that's the case, there are infinitely many solutions given by, well, the equation of the line itself. All right? That's basically it. So how are we going to do this? What is the process? Some of you may have seen this before in a previous math class. There's essentially two ways that we are going to discuss, or I should say, well, two ways we're going to explore. One way we're going to discuss today. One of them is called substitution, and the other one is called elimination. So let me kind of run through what goes on in those two cases. Substitution involves solving one of the equations for one variable and then substituting the resulting formula in the other equation. So you can think about, let me go back, solve this equation for, let's say, y. And then once you have this in the form y equals something, take that expression and replace this y with that. And then you will have an equation in one variable that you can solve using more elementary techniques. Yeah. So once you solve that, plug that result into either original equation or their equivalents, and then solve for the remaining variable. That's the idea. Now, elimination is often easier, or maybe takes fewer steps, I could say, or leads to somewhat less messy calculations. So, elimination involves manipulating one or both of the equations until adding or subtracting one equation to or from the other results in a cancellation. So, what you're looking for is a cancellation. And that cancellation will eliminate one of the variables. So let me say that again. Elimination basically means massage one or both of the equations and then add them together or subtract one from the other. But your manipulation should make it so that when you add them together, one of the variable terms is canceled and disappears. Because when you do that, you'll be left with a single equation to solve for a single variable, and you can use elementary techniques. Once you solve that, plug that result into either original equation and solve for the remaining variable. All right, so that's a lot of words. That's a lot of me just saying out loud what we're going to do. Let's do an example. Let's do an example and I'll walk you through it, okay? Um, if you've done this before, great. I know it gets emphasized in a lot of American high schools, so if you've seen this before, great. Just refresh your memory from what you did then, and we're going to do it again here. Okay, so let's try to solve this system of equations. This describes a line. This describes a line. We want to know if and where these two lines intersect. All right. So we're going to use elimination. I'm not going to use substitution. But what I'm noticing when I examine these two equations is if this sign was positive, or if this sign is positive, then if I were to add these two equations, I would get a cancellation, right? These two terms have the same size, 3y, 3y, but the sign is also the same. If the sign was opposite on just one of these equations, and then I added them together, they would cancel. So that's what I'm going to do. I'm going to basically massage one of these equations to get this sign to be a positive, and then I'm going to add the results. Which one do I do? Here we go, top. I'm going to multiply the top equation by -1. And then when I do that, the signs of these will be opposite, and then I'll add them together. Here we go. So here I'm multiplying the top equation by -1. And then when I do that, I get this system. These are equivalent systems. That's why I'm using the double-headed arrow. That means equivalent, right? These two things are equivalent to each other. But the good news is, look, now this is a positive 3y, this is a negative 3y. So I'm going to add these two equations together, and these will cancel. And that's what I'm doing right here. Okay, so I'm going to add these two together. In fact, let me do this. There we go. I'm adding those two equations together. Negative 2x plus 6x is 4x. Positive 3y minus 3y is 0. Negative 5 plus 12 is 7. And now I have a single equation in one variable. There it is, single equation in one variable. Now I can solve it for x. So I'm going to solve this for x, and that gives me x equals 7/4. Boom. So now I've got the x coordinate of the point of intersection. Now I need to find the y coordinate. Good news, I can take this x value and I can plug it in to any one of the equations or any manipulation of these equations to find the y value. All right, you get some flexibility now. um, what I'm going to do is this. I'm going to massage the second equation a little bit. I'm going to divide the second equation by 3 and then plug in x. So here's the second equation. I'm going to divide both by 3. So divide by 3, both sides by 3, right? So then I get 2x minus y equals 4. Now I'm going to substitute x. So x equals 7/4. And now I just simplify and solve for y. So simplify this. This is the dot, 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 continues right here. 7/2 minus y equals 4. 7/2 is 3.5. Makes it a little easier for me to work with. I'm going to subtract 4 and add y. So 3.5 minus 4, that's -0.5. And y is y. So now we got the y coordinate. Y equals -1/2. All right. Okay, so what did we just do? Well, we found the solution set to this system of equations. The solution set is this single point. So this is the point where those two lines intersect right there. Sorry, let me say this. This is the point where the two lines intersect, and this is the solution set to the system, the collection of all solutions to the system. Let's look at a picture now. Boom, zoom in. So I've got both the lines graphed. 2x minus 3y equals 5, which is right here. Actually, yeah, I'll say right there. And then 6x minus 3y equals 12 is right there. Where do these two lines cross each other? Right at that point. X equals 7/4, y equals 1/2. And that's solving a system of linear equations in two variables, two equations in two variables. Okay, but that's it. Now it's time to play. So I will try not to ramble too much longer. I know this has been a long lecture, so I thank you for bearing with it. It's a ton of information packed in, but it's kind of like all the information about lines and linear functions and systems of equations that we're going to need. All right, so I'll end it there. Thank you again for listening, and I will see you next time in section 3.2. Have a good one, everyone.